We're going to look at how to balance nuclear reactions in this video. So let's start with a review. Where are the parts of the atom? Protons and neutrons are in the nucleus. So protons, neutrons. Electrons are in the outside in the electron cloud. So really when we're talking about nuclear reactions and nuclear equations, we don't really care about these electrons. We're really worried about what's going on in that nucleus, so protons and neutrons. So there's two forces that hold together the nucleus, well, two forces in a nucleus. One is electromagnetic and the other is strong nuclear. The electromagnetic force, it's the idea that you have positive and positive because protons are positive and they are going to repel each other. That's what those blue arrows are showing, electromagnetic forces. Positive charges want to repel, like repel. But we have these strong nuclear forces, which is just forces between the particles, even positive-positive. And these strong nuclear forces are what actually hold together the nucleus of an atom. So which are stronger? Obviously, the strong nuclear forces have to be stronger because they are responsible for holding this nucleus together. So first, what is radioactivity? Radioactivity is any process where the nucleus emits particles or energy. So whenever you think about like a radioactive material, the reason why it's radioactive is because the nucleus is changing in some way. It's either releasing energy or it's actually releasing particles of some kind. An example is uranium-238. Uranium is what is used in a lot of nuclear power plants. It's also what was in nuclear bombs and other weapons, nuclear weapons, because there's just so much energy that is released by the radioactive decay of uranium that you could actually harness that into either a weapon or actual energy to then power cities and states and all. So uranium definitely emits radiation. And here radiation can either be particles or pure energy. The eventual end of a radioactive decay chain, so that's all the steps that happen, all the different releases, is to form a stable atom. So for any radioactive material that's really large up here towards uranium, it will always go to lead. Lead is the stable atom that is the largest after all of these radioactive materials. So uranium, plutonium, all those things will eventually lead to lead. Uranium-238 specifically leads to lead-206. Now these numbers, 238 and 206, those are the atomic weights. And if you remember back, atomic weight is protons plus neutrons. And that's how we get our different isotopes. The process for uranium-238 takes about 5 billion years. So for uranium to go from uranium-238 to lead-206 takes 5 billion years. This is also why if you have a nuclear power plant, it can be really dangerous to deal with the nuclear waste associated with them, is because it can take billions of years for that material to then completely degrade. We have to find somewhere to put it. So the three kinds of radioactive decay, we have alpha, beta, and gamma. Alpha decay is whenever you release a particle, and this particle is specifically a helium atom. So a helium atom. This helium atom has 2 protons and 2 neutrons. So the nucleus is releasing 2 protons and 2 neutrons. The helium atom is called an alpha particle, and this is also the lowest energy. So these are not very dangerous at all. Alpha decay actually can be stopped by even a plain sheet of paper. So your sheet of notebook paper will protect you from alpha decay. So you are not in any danger with alpha decay at all. The second kind is beta decay. And beta decay also releases particles from the nucleus. So a radioactive material will release a neutron, and this neutron will split into a proton and an electron. So the neutron splits into a proton and an electron. The proton stays with the nucleus. The electron is released. So proton stays, electron is emitted. And the electron is what you call the beta particle. This is higher energy than alpha decay. So this is increasing in energy in terms of how much energy is released. Beta decay will still be stopped by skin. You probably want to use something like wood instead of a piece of paper, but it's still not very dangerous at all. Now the most dangerous kind is gamma decay. And if you remember from electromagnetic spectra, gamma rays, which is what gamma decay releases, are the highest energy, highest frequency type of wave, very dangerous. So release of high energy electromagnetic radiation. So this is not changing the nucleus, just releasing energy. So now let's look at how the nucleus and the particle that is released is going to change, specifically looking at number of protons and neutrons. So for alpha decay, you take your original nucleus of your radioactive substance and you're releasing a large particle. And here this particle contains 2 protons and 2 neutrons. So 2 protons and 2 neutrons. Therefore, the original nucleus is going to decrease by 2 protons and decrease by 2 neutrons. What's released is this alpha particle, which is this helium atom, and some energy, of course. So here you start with 238, uranium-238. 238 includes protons and neutrons. So if we're decreasing by 2 protons and 2 neutrons, that 238 should be going down by 4. And that's what we see, is that 238 goes to 234. This number, the 92, is the atomic number, which tells you the number of protons. So the protons change from 92 down to 90. This is what changes the element, is that number of protons. And you also release this alpha particle, this helium atom, with 4 total weight and 2 protons. For beta decay, you take your original nucleus and you're changing 1 neutron into 1 proton and releasing an electron. So you're increasing the number of protons by 1 and you're decreasing the number of neutrons by 1. So decreasing neutrons, increasing protons. What's released is the electron. So here if we start with carbon 14, so 14 is the number of protons plus neutrons, and then 6 is the number of protons. We're increasing the protons by 1. That's why you see down here that nitrogen is our new element. It has 7 protons. But notice the weight doesn't change. And that's because we're just changing 1 neutron into 1 proton. And of course releasing energy. Now gamma doesn't change the nucleus at all. It stays completely intact. So no change in protons, no change in neutrons, just release of high amounts of energy. And that's what we see here is a little wave. Alright, so here we go. We're going to balance our nuclear reactions. What we need to do is know our 3 types of decay. So let's write those out so we've got them. We have alpha decay, and alpha decay releases a helium atom, which is an atomic number of 2 and an atomic weight of 4. Beta decay is the release of an electron. But what happens is a beta particle takes a neutron and creates a proton. So for beta, the beta particle releases the proton, changes the neutron to a proton, which means we're losing a proton as a beta particle, but there is no change to the mass or the weight. The weight does not change, but what happens is this beta particle is essentially losing a proton. Gamma, so for gamma radiation, there's no change in the number of protons, and there's no change in the number of, or the weight. So there's no change at all. So here's the easiest way to do this. If you use the idea that alpha is a helium atom, beta will increase the resulting element by 1 proton, which is what this -1 means, and then gamma doesn't have any change. Then all you have to do is just the math. So here, in our first one, we have a weight of 238, and we're going to 234. The difference there, because left and right have to be equal, means we need a weight of 4. For the atomic number, we have 92, and we have 90, which means to make it equal on both sides, we need a 2. Hey, look, it matches up with helium. And so this is alpha decay. For the second one, our beta means that we're not changing our weight, but we are releasing a proton from the beta particle. So 234 plus 0 gives us 234. 90, and we have a -1 here, so 90 has to equal -1 plus some number, means we're going to have a 91 here. 91 minus 1 gives you 90. That's going to be protactinium. So lo and behold, if you notice, this product is this reactant. So what we're doing here is we're actually looking at the first 3 steps of how uranium-238 changes. So let's look at our third one here. We have 234, and we have 234 on this side. That means we have a 0 change. We have 91 on the left, we have 92 on the right. So to equal that out, we have to have a -1. That means beta decay. The last one here, you should notice that both sets of numbers are the same, 40, 40, 19, 19, which means there is 0 change, so this has to be gamma decay. And the idea is these usually will have a star next to them, and the star means it's higher energy. And so here, this higher energy star is what is released as the gamma radiation, and you're left with a lower energy of the exact same particle.